So I'm going to try to give you some examples and kind of give you an idea of saying, okay, we have this network model, how you start with an area of application, some kind of network that you actually want to compose, and how do you sort of build that back to get you the right network model, which will give you the right operator to express composition in this framework. And so just to let you know, right, sort of in theory, the way you go about constructing network operands is that you first construct a functor, then that gives you a category, then that gives you an operand, and then once you have an operand, you can say, well, we have all these great algebras, right? But when you're actually doing this in practice, right, you're sort of working from the other direction. In practice, you have some kind of network node that you want to actually compose. And so the challenge really is to extract the essential features of composition that you need in order to model composition. Sort of in this network model setup where you're going to build network operands, you need to know how you're going to place the networks you're interested in side by side. Often that has this easy answer, the 2-rock answer that John was talking about. But then the crux of it is you really want to know, well, how are networks going to change as you have these operations whose purpose is to overlay edges. By building these features into the network model, then you actually get an operand that provides these formal instructions to compose the network you're interested in. So we'll go through some examples coming from this cascade work. And so this first example was sort of what got this whole ball rolling, and it was for range-limited communication. So you wanted a way to represent range-limited communication. So what were the networks you're actually interested in? Well, say each vertex in your network actually has an attribute that gives you its location in the plane. So for instance, in this picture with this yellow network, we've got 5 nodes, and we can think about those being in the plane. And then you want these edges to actually represent two-way communication being possible between your nodes in the network. So you put in this constraint that says, all right, well, we're going to have a length limit of L that's going, and we're not going to be able to have edges that are longer than that length. And so in this example, say we cook it up so that your nearest neighbors are okay here in the graph, but these farther distances don't meet the edge limit. Okay, so then how does that fit into asking these two questions? Well, you say, okay, how do I put range-limited networks side by side? And you say, well, you can do this just when you got a network over here, you got a network over here. That's easy enough. Then you're saying, okay, well, how do these networks change as you overlay edges? And this is what John's talking about. You're saying, well, it's perfectly fine to say I have this little this simple graph that says, well, you should put in a link over here and put in a link over there. That makes sense. And in that monoid, right, the order doesn't matter. You actually think about using a graph, it's near a monoid structure. But anyways, when you're actually doing this, you have some existing network which has some communication links in it. And then you're saying, okay, I attempt to add from 2 to 3, and that meets the range limits, that goes in. And then I attempt to add from 1 to 3, and that doesn't meet the range limit because that's too big. And so it doesn't go in. That's how you actually act on these networks. And what this means really is that simple graphs are sufficient to give instructions to compose these range limits. You have instructions on how you want to have these things together. But in order to know what actually happens, you actually have to look at the attributes of a particular system. Okay. So what's another example? So John was talking a little bit about how you could sort of try to bootstrap up from these, sort of these simpler models for composition to more complex ones, linking them with maps of algebras. And so for this cascade challenge where we're doing search and rescue, that's our application area, right? We want to design and task a system that's going to effectively rescue isolated persons. And so when you're designing the networks, you have these vertex colors, which when you're trying to set up this framework for design, you have basis and platforms and other things that you need to put in there that says, well, this is how things are laid down. This is how things are sort of statically designed in order to meet this SAR need. And then you have a bunch of state attributes for these vertices. So bases have locations, you might have speed, range, other properties of your particular platforms. And then you have constraints on these directed edges that do things like assign assets to bases, and they're constrained by capacity, runway length. There might be certain assets that it just doesn't make sense to put on base. Okay, and so then what are you doing? The whole point of this design network is you're trying to make a design decision that says, okay, I need to select where to put assets at bases based on my anticipated need for something. And then once I actually get going with a mission, right, I'm going to have to actually assign these assets to tasks that will actually rescue isolated persons that are out there. Okay, and so what do? Is you take, you have these notions of networks that you already have for design, and then you need to add more vertex colors and these task edges that will define what you want, and you want to make sure that it's consistent with what you already have. So for this point, you're saying, well, we need to add, for example, IP events, right? Because we didn't have those based on our anticipation. And then we also want to add these edge colors for different task relationships, like maybe the helo is going to go rescue this particular isolated person, and you have other assets might be providing escorts to force package. And as John was talking about, in these range-limited networks, you can put some constraints on TAC right in the algebra. So just like range-limited network, you can say, okay, maybe this, as John was saying, maybe this helo is really, if it's at this particular base, maybe that base is really too far from this particular IP for it actually to make sense. But a little bit more interesting is encoding constraints on these instructions. So what you would like is whenever you're looking at instructions, you don't want the instructions to not make sense, right? And so John was talking about this one task at a time limit that you would like. Another thing that was in this particular version of the problem was that assets that shared the same base were actually allowed to coordinate to rescue a particular IP. And this is where you have these linked effects that you're trying to put right into the syntax. So each one of these edges by itself, right, it makes sense to put a helo on a base. It makes sense to put a helicopter on a base. It makes sense to decide that this helo is actually going to recover this IP. But what doesn't make sense, at least in this particular framework, is to have helos for two different bases going this IP, at least in this concept of operation, right? And so what you want it to be the case is that when you do those iterative operations in that order, you don't actually put link in the syntax, not just in the algorithm. And this is, illustrates that you really can code this up in a way so that you can deconflict things that you don't even want to have as instructions for how to compose some network. So that's a nice feature. Another feature that John may have mentioned is that it's actually kind of cool to overlay that, right? And so this next example that I'm going to give is going to talk about, it's really going to be about something that people, engineers have already used overlay of dynamics in a certain way to control the behavior of drones, for example. And this is something that fits into our framework, but is maybe a better illustration of why would overlay be sort of a useful thing that sort of goes beyond the other features we've talked about. Okay, so suppose you want to coordinate the behavior of two UAVs with a single location attribute. So one real simple cooperative behavior is to have them to head towards each other, right? And so you can actually formalize that by saying, okay, well, that defines vector defined in this way. Okay, and so if you want to use simple graphs to say, okay, this is going to tell those UAVs to do this behavior, you can say, okay, this simple graph where they have an edge between them is saying, okay, you guys are working together. Or if there's no edge, you can say, well, they just stay put. You don't have, it's just the vector field where things constant, independent of the state. So the cool thing about this, right, is that you can actually, you can actually overlay. That's not working? That's not working. Okay, so this is supposed to be an animation. But anyways, but what's happening here is that to coordinate the behavior of these UAVs, you can actually overlay these interactions, right? So in this particular case, right, you have these two pairwise interactions that are coming from these two pairs, these two edges, right? And so if you just add those vector fields, that will give you behavior for the entire network that beats inconsistency. So in this particular setup, if you have these three UAVs starting in the start position, they are going to go towards central. And there's lots of known results that show that that overlaying is useful. Basically, for instance, you get global stability for any connected network with these dynamics, and there's further techniques available from people who thought about these kinds of control problems for controlling formation, trying to maximize sensor coverage and that sort of thing. And so sort of our perspective is that, there's many ways to overlay dynamics with network operads, and so we're going to try to find the ones that fit our problem as best we can. And so this is just an example of saying, well, if we work this operad based on simple graphs, this is, the slightly more general way you could hook up to overlay edges, and you can even start, using other notions of sum. So in the sum, right, you can use other commutative modeling structures, and that becomes useful if you want to do something like enforce a max speed for the UAV. For other kind of applications, you can sort of build that into the way you're saying, well, I have one vector field, I have another, I'm going to overlay them, but I get to define how exactly that works. And so our current cascade work, one of the things we're interested in is combining decentralized control of formation by having some UAVs that are sort of leaders, and then these decentralized, these other UAVs, the minions, are going to try to anticipate coverage for our functions so that when an IP event happens, there will be someone close by. So that's what I have. If you want to see a little bit more about some of these control methods, since this is relatively recent stuff coming out that John and I are talking about, you can look at here.